Dear students, how to perform deformation and stress analysis in the cantilever beam subjected to point load using ANSYS APDL software. We will discuss in this lecture video. So this is the problem given for finding out the deformation and stress induced under the loading condition 800 pounds. Okay. So first we can convert all the units, all the given units to SI unit. So the problem will be like this. So first we can model the given cantilever beam structure in the APDL software, after which we can give the loading condition, then we can solve it. Okay, the step-by-step procedure to solve this problem using ANSYS APDL we will discuss. So first we have to define the type of problem. So this is a structural problem. Then preprocessor element type. So this is a beam type problem, 2 node 188. Material properties. So we can assume the material of the given beam element as steel. So the Young's modulus of the steel material can be assumed to be 2 into 10 power 5 Newton per mm square. E5. Then sections, beam, common sections. So in the APDL program, it will be programmed like this. That is, the actual breadth and width of the sections will be programmed in the APDL software as, breadth and height of the actual sections will be programmed in the software as height and breadth. Okay, so we have to provide the breadth value as height and height value as breadth in the APDL software. So here in the given problem, both breadth and height of the problem, height means thickness of the given beam is same to be 100 millimeters, so there is no problem. Directly we can feed the breadth and height values as inputs. Then we can model. So using nodes and elements we can model the beam, as well as we can use key points and lines commands to model the beam. So for the given problem we have we can model the given beam with the use of key points and lines commands. Okay, key points in active CS. So the first nodal point can be set as origin. Okay, the leftmost point. Okay. Second point. So from the left, if we model, and the second point will be in the position where the point load is acting. Okay. So from the right end, the distances are mentioned in the problem. So the second nodal point, second key point can be set at a distance 4267.2 minus 3657.6, so 609.6. So along the x-axis the beam is getting distributed. So remaining coordinates will be 0. Third key point, the end of the beam, the right extreme, that is at 4267.2 millimeter. Okay. So now we can connect these key points using lines option, lines, straight line. So we can select the key points to connect using lines. Okay. So now with the aid of the features in finite element analysis, we can subdivide the entire element into convenient number of elements. For that we have to go with the meshing option. Okay. So mesh tool. Now we are going to subdivide the elements which are represented using lines option. Select the lines to be meshed, first to be subdivided. Okay, convenient number of elements say 100 number of subdivided elements. Okay, now the entire lines which we have selected got subdivided into 100 number of elements. Now we have to then mesh. So mesh, select the subdivided elements. Okay, now the entire element that have been subdivided now got meshed. Okay, so go to solution to define the constraint as well as loading condition. So define loads, apply structural displacement now on key points, because the entire element has been defined, has been modeled using key points. So the rightmost extreme as constraint in all the directions, that is a fixed support. Then force moment on key points. So this point is loaded with a point load in the negative y direction. The value Fy is minus 3558.58. So now the entire problem has been modeled. Now we can solve the problem using current load setup. Solution is done. So to read the results, go to General Post Processor, plot results, contour plot, nodal solution, DOF solution, displacement vector sum. Okay. So the maximum deformation experienced by the given cantilever beam under the loading condition is observed to be 43.5464 millimeter. So to predict the stress induced, we have to first define the stress model using element table, define table. So with the aid of sequence number, we can define the element tables. Okay, so for axial bar elements, to predict the axial stress, we have to select the sequence number LS1. Here in this case, under on beams under the loading condition, that is in transverse direction, bending stress will get induced in the beam. So the sequence number for defining bending stresses in the beam is SMISC 32 in the ith key point, and for the jth key point SMISC 37. Okay. So now we can go to plot results, line element results. For the ith node SMISC 32, for the jth node SMISC 37. Okay, so this is the stress induced plot. Here we can see that the maximum stress induced is obtained at the fixed position of the cantilever beam with the magnitude 77.7047 Newton per mm square, that is megapascal.